Okay, in this video, we're going to be dealing with Newton's method, this section 4.8. And what Newton's method is, it's just a method of finding the approximate root or the approximate zero for any polynomial function. This method came about back years ago when graphing calculators were not invented at the time, so they came up with that particular method to come up with an approximate zero for that polynomial function. Okay, now here we can derive Newton's method geometrically. Here we're assuming that r is going to be the root of the function f that we wish to approximate. That means that f of r will be equal to 0. So here's a graph of just that. This is the first page of your handout. Well, here we've got x of 0 here that we're going to use as a initial approximation to r, and we're going to pick a point. We're going to find out what that point is at x of 0. So when we do that, it's going to be here on this particular graph of y is equal to f of x. So this right here will be x of 0, f of x of 0. And in this case here, if I draw a line that's going to be tangent to that particular curve, which is going to be this right here. Let's say this is the tangent line, and it touches the curve at that particular point. And as you can see here, that tangent line is going to cross the x-axis at this particular point right here, which I'm going to call x of 1. Okay, now we're going to find the point where x of 1 is on the graph of y equal f of x, which is going to be this point right here. And then I'm going to draw another tangent line through that particular point. So here's the tangent line. So this second tangent line crosses the x-axis at this particular point, which I'm going to call x of 2. Now the idea here is I'm going to keep drawing tangent lines until I'm able to get that tangent line to be the x-axis, which is going to be the point where r is going to be. That's going to be the 0 of that particular function. So here, let's say this point at x of 2 is on the graph here. And then we draw another tangent line. Okay, so that's the tangent line to this particular point, and that tangent line crosses the x-axis at that point, which I'm going to call x of 3. And I keep drawing a point on the graph where x of 3 is at, and keep drawing tangent lines like this until this tangent line ends up becoming the x-axis, and that will be the point where the root of that function is going to be at r. Okay? And here on the second page, they do give you that same illustration that I just went over with you. Okay? All right, now here we can derive the Newton's formula, or Newton's method that he uses by using point-slope form. Y minus y sub 1 is equal to the slope times x minus x sub 1. Okay? All right, so here we got we draw a line that's going to be tangent to the point, to the curve at the point x of n, comma, f of x of n. So using that point slope form, this is going to be y minus y sub 1. That's going to be this f of x sub n. And that's equal to m, which is going to be the slope of the tangent line. But the slope of the tangent line is always going to be the first derivative of x at x of n. The first derivative of x of n, that's this. And then that's multiplied by x minus, and I'll let x1 be the x of n. Okay? Now, in this case here, we're trying to find out what r is. Here, the y value is 0. That's your x-intercept. So here, this y is going to be 0 minus f of x of n, and that's equal to f prime of x of n times x minus x of n. Okay. So here, this will be negative f of x of n equaling to f prime of x of n times x minus x of n. Now here, the objective here, I want to solve for x. So what I need to do here is divide both sides by f prime of x of n first. Okay, so what I'm going to have is x minus x of n equaling to negative f of x of n divided by f prime of x of n. And then I'm going to move the x of n over to the other side. So this means I'm going to have a positive x of n, and this will be minus f of x of n divided by f prime of x of n equaling to x. Okay, now, if I let x, if I call that x of n plus 1, which is going to be the next, the new approximation, this is what I'll have. And pretty much this is down here at the bottom, but I'll go ahead and write it again. That x will be replaced with x of n plus 1, and then that's going to be equal to what I came up with. X of n minus x of f of x of n divided by f prime of x of n. Okay? So this right here represents Newton's method. Okay? Okay, so that's Newton's method for approximating the roots of f of x sub 0. And here's a better illustration of that. And the procedure is going to be this. You're going to choose an initial approximation of x sub 0 as close to the root as possible. Now, in the examples that we'll do, you'll be given what x sub 0 is to start off with. And then, number 2, for n is equal to 0, 1, 2, and so on, this is your Newton's method formula. X of n plus 1 equaling to x of n minus f of x of n divided by f prime of x of n. And that's with the provision that the first derivative at x of n is not equal to 0. And then you're going to end the calculations when a termination condition is met. And what do I mean by a termination condition? That means if whatever you come up with for x of n sub 1, x of n plus 1, if that value remains the same, then you can end the calculations here. Okay? So here, this is an example of a repetitive loop calculation called an iteration. And the most efficient way to implement the method is with a calculator or computer. The method is also included in many software packages. And I'm sure the graphing calculator does use Newton's method when you're finding the zeros of any polynomial function. So let's start off with this first example. Here you're going to write a formula for Newton's method and use the given use the given initial approximation to compute the approximations x1 and x2. So here we got the function f of x is equal to x squared plus 4x minus 32. And your x sub 0 they're giving you to be 6. Now we can use that table right there if we like, but yeah, we're going to use that for now. And then the other examples, I'm going to show you how to use the graphing calculator to come up with your other approximations like x1 and x2. Okay, first of all, let me write this in the form of f of x sub n. Because in the homework, they're going to want you to choose the formula for Newton's method using f of x sub n. So if I replace each x with x sub n, this is what I will have. X sub n, that's going to be squared, plus 4 times x sub n minus 32. Okay, that's what f of x sub n is going to be as this formula. I need f prime of x sub n as well. Well, I need to know what the first derivative of x is. So f prime of x, that's going to give you, in this case, 2x plus 4. So the first derivative of that function is going to be 2x plus 4, and then replace the x in that first derivative with x sub n. So this will be 2 times x sub n plus 4. Okay? Now the formula for Newton's method, I'm going to write that at the bottom. This will be x sub n plus 1. And that's equal to x sub n minus, the numerator is the f prime of x sub n. That's this right here. X sub n squared plus 4 times x sub n minus 32. Now this part is going to be over f prime of x sub n. That's this part right here, the 2x sub n plus 4. So it'll be 2 times x sub n and then plus 4. Now keep in mind that only f prime of x, f of x is going to be in the numerator and f prime of x is in the denominator and not be x sub n. Okay? And now, let's let's use this formula to find the initial approximation for x1 and x2. Well, I know x sub n is 0, so this is x sub 0, which is of course 6. Now, the way I broke this up, this first column is going to be what f of x sub n is, and then this is what f prime of x sub n is going to be, and then this column, I'm going to divide these two columns here to get this, and then whatever this is, I'm going to subtract it from what x sub n is, which is a 6, to get that last column. Okay, let me show you what I mean here. F of x sub n. Well, here, your x sub n is going to be 6. So to get this, I just substitute each x in f of x with 6. So this will be, in this case, 6, and then that's going to be squared, plus 4 times 6, and then minus 32. And then hit enter. That's what f of x sub n is. At 6, it's going to be 28. And now for f prime of x sub n, well here, your x sub n, that's still 6. This is your f prime of x function here. That's the 2x sub n plus 4. And x sub n is going to be 6. So here, this will be 2 times 6 plus 4. Just substituting x sub n with that 6. That's going to give you 16. And now for f of x sub n divided by f prime of x sub n, I take this number divided by that number to get this space, this blank space in the column here. So 28 divided by 16. That's going to be 1.75. Okay. So now, x of n minus this. This part I got is 1.75, and this is x of n. So I'm going to do 6 minus the 1.75 to get this number right here. So 6 minus 1.75 would give me 4.25. Now that 4.25 represents what x sub 1 is going to be. Okay? Because for the next row here, your n is going to be 1. And now your x sub n will be this number right here, 4.25. That goes here. Because whatever you get here will go here under x sub n. And then we'll do that process over here. So now, f of x sub n, I'm going to replace each x within the f of x function with 4.25. So here I'm going to have 4.25, and I'm putting this in parentheses, and that's going to be squared, plus 4 times 4.25, and then minus 32. So here that value will be 3.0625. And now for f prime of x sub n, that's the 2x plus 4. Replace that with the 4.25. So now you're going to have 2 times 4.25 plus 4. And that value is 12.5. Now we're going to do f of x sub n divided by f prime of x sub n. So that means I have to do this number divided by that number right here. 3.0625 divided by 12.5. And that would give me 0.245. And now for the x sub n minus f of x sub n divided by f prime of x sub n, here your x sub n, that's the 4.25, and then we're going to subtract 0.245 from 4.25. And I get 4.005. Now that 4.005, that's going to be the value of x sub 2. And here we can stop right here, because we only want the approximations for x sub 1 and x sub 2. And we have that. Yeah, x sub 1, that's 4.25, x sub 2, 4.005. Okay, so that's how we apply Newton's method to do these type of problems here. Okay. All right, now let's look at this example, example number 2. Here we're going to write the formula for Newton's method and use the given initial approximation to compute the approximations x1 and x2. And in this case, we got 3e to the negative x minus 14x. Okay, let's find out what f of x sub n is, because they're going to want that in the homework when you choose the equation. Okay, replace each x with x sub n in f of x. So this will be 3e to the negative x sub n minus 14 times, and that x will be replaced with x sub n. Okay. Now, this one, I'm going to need the derivative of f of x. So in this case here, I need to find f prime of x. For the 3e to the negative x, I'm going to bring down the 3. The derivative of e to the negative x will be e to the negative x. That's the easiest derivative, but I have to take that inside derivative. The derivative of the negative x is negative 1. So I'm going to put a negative sign in front of the 3. And then minus, the derivative of 14x will be 14. So now, f prime of x sub n will be this. We got negative 3, and then e to the negative x sub n minus 14. Okay, so my x sub n plus 1 that I'm going to write down here at the bottom, that formula will be x sub n minus, and of course that's f of x sub n, and then divided by f prime of x sub n. So that's just x sub n, and then minus f of x sub n is that 3 e to the negative x sub n minus 14 x sub n. Now this is going to be divided by negative 3 e to the negative x sub n minus 14. Okay, that's going to be the formula that the homework problem will be looking for. And now we can use this table to find out what x sub 1 and x sub 2 are going to be. Now here, they tell you x sub 0 to use is ln of 5. So n is 0, so that means x sub 0, that's the natural log of 5. And now to evaluate f of x sub n, we use this f of x sub n formula here and replace each x with ln of 5. Okay, now let's see what we can do here. We're going to have 3, and then for the e, second ln, and then we press the negative key for the negative, and then for ln of 5, I'll just go ahead and type ln, and then 5, close the parentheses, and then use my down arrow key to get out of it, or use the right parentheses, and then minus 14, and then x sub n, well, I do times, x sub n, that's going to be the ln of 5, which I'm replacing. And here I have to close the parentheses twice for the ln and then for the left parentheses here. And then hit enter. Let's say I want to round that off to, I'm going to say 6 decimal places here. So in this case here, this would be a negative 21.9321131. Okay? Because here's a 6 decimal place, that's a 0. The 7 will increase that 0 to a 1. And then f of x sub n, f prime of x sub n, that's this formula right here. Replace that with ln of 5. So here, this will be negative 3. And then for the e, second ln, and then the negative key, and then type in ln 5, close parentheses, use your right arrow key or close your parentheses, minus 14, and then hit enter. That would be negative 14.6. And then for your f of x sub n divided by f prime of x sub n, we take this number divided by this number. So it'll be, let's see, negative 21.932131 divided by negative 14.6. And I'm going to get 1.5022, let's see, 01, rounded to 6 decimal places. And then for the x sub n minus that quotient, I'll take this number subtracted from what x sub n is. Okay? So your x sub n, that's going to be ln of 5, close parentheses, minus this decimal value right here, 1.502201. And this will be 0.10737, rounded to 6 decimal places. So that value right there represents what x sub 1 is going to be. Okay. So n is going to be 1 here, and then this will be 0.107237 to 6 decimal places here. And then I'm going to go through that process to come up with what x sub 2 is going to be. Okay. So this is what f of x of n is equal to. So I'm going to replace the x with that decimal value here. So this will be 3, and then second ln for the e, and that's going to be to the negative x, which is going to be 0.107237, and then I'm going to use my right arrow key or close the parentheses, minus 14 times 0.107237, close parentheses, and then hit enter. And that's going to be my decimal value to 6 decimal places. This will be 1.193620. 1.193620. Now for the f prime of x of n, I'm going to use this formula here for f prime of x and then replace that decimal value for x of n here. So in this case here, this will be, let's see, negative 3, and then for the e, second ln, and then to the negative, and then type in 0.107237. Close parentheses, or use the right arrow key, and then minus 14. So this will be negative 16 point, let's see, 694938. And then for f prime of x of n divided by f prime of x of n, I take that number divided by this number. So I'm going to take 1.193620, divide that by negative 16.694938, and to 6 decimal places, that's going to be a negative 0.071496, because this is a 6 decimal place, the 9 changed it to a 6. And then finally, x of n, that's this number right here, minus this number right here. That's the f of x of n divided by f prime of x of n. So it'll be 0.107237 minus a negative 0.071496. You get approximately 0.178733. That's going to be what x sub 2 is going to be. And we're done right here with that problem, because we only want the approximate x1 and x sub 2 for that particular function. Okay. All right, now let's look at example 3. Now this one, we're going to use the graphing calculator for that one. And I'll use the graphing calculator for the other examples as well. So here we're going to use the calculator or program, graphing calculator more specifically, to compute the first 10 iterations of Newton's method when they are applied to the following function with the given initial approximation. In this case, we got f of x equal to x squared minus 23, and the initial approximation will be x sub 0 equaling to 5. Okay? So we'll know what x1 is from here, x2, then x3, x4, x5, x sub 6, x sub 7, x8, x9, and then x sub 10. I think this goes up to x sub 9 because we know x sub 0 is going to be 5. All right, now I'm going to show you how to type all this in the calculator here, but before we do that, we need to know what f of x of n is going to be. Or just simply replace the x with x of n. That's just going to be x of n, and that's going to be squared minus 23. And I need the derivative of that particular function. Well, if f of x is x squared minus 23, then f prime of x would just simply have to be 2x. And then f prime of x of n will be just 2x of n. And then in this case, x of n plus 1 would be, of course, x of n minus f of x of n. That's going to be that x of n squared minus 23. And only this will be divided by what f prime of x of n is, 2x of n. Okay, now I'm going to show you how to enter this into the graphing calculator here. Now, we got x of 0, and that's equal to 5. So in your graphing calculator, you're going to type in the number 5, and then there's a button that says STO, and then you're going to press the button that says XT theta n, and then press enter. So these are the keystrokes here. So I'm going to clear this out. I'm going to type in the number 5 and then press the STO button, which is on the left-hand side of your calculator right above the on button. STO to store. You'll get the right arrow, and then you're going to press XT theta n because you want to store this in X. And then you're going to press enter, and it's going to give you the number 5 back. Alright, now the next thing I'm going to do here is type in this equation that's after x of n plus 1. But I'm going to treat those x of n's as x's. Okay? So for that formula, this is what you're going to type. You're going to press the xt theta n button for the x. That's for this x right here. And then minus. And then I'm going to use the left parentheses key here because I'm going to put all of this in parentheses. And then for the x of n squared, I'm going to press xt theta n for the x, and then press the x squared button for it to be squared, and then minus 23, and then your right parentheses, you want to close that off, and then whatever this is, you're going to divide that by the 2, and then xt theta n for the x. Oh, and before that, you want to do left parentheses. I forgot that. So left parentheses first, and then 2 times xt theta n, and then your right parentheses. Here I'm going to put the numerator and the denominator in parentheses to be on the safe side. And then after which, you're going to press the STO button to store it, and then xt theta n for your x, and then you're going to press enter. Okay. Now I'm going to go ahead and do this on the calculator so I'll be caught up with where you are. So in this case here, you're going to type xt theta for the x, and then minus, and then left parentheses xt theta n for the x, and then your x squared, and then minus 23, close parentheses, and then divided by, and then left parentheses 2 xt theta for the x, and then close the parentheses. and then press the STO button to store it, and then XT theta for the X, and then hit enter. What that's going to do, it's going to give you what X sub 1 is. We know X sub 0 is 5, so that 4.8, that's what X sub 1 is going to be. Now to find out what X sub 2 is, go ahead and press enter again. It'll give you that. Now let's say the 6 decimal place, this will be 4.757958. $4.795833. I'm rounding to 6 decimal places. And then for X sub 3, we press enter again. So it'll be this number, 4.795832. If I'm rounding it up to 6 decimal places, because that 1 is a 6 number after the decimal point, the 5 makes the 1 a 2. Hit enter again. And as you can guess here, that number remains the same. That means that number right there represents the 0 for the function f of x is equal to x squared minus 23. So we know that's one of the zeros, but we're just dealing with this one right here for x sub 0 equaling to 5. And we can keep doing that, and you can see that it's going to still remain the same. X sub 6, same thing. And then X sub 7, still the same thing. So you can see that this particular Newton's method is going to be converging to this particular value, 4.795832, rounded to 6 decimal places here. Okay, so these are the first 10 iterations here, and that includes x sub 0 being equal to 5. And even if I go to x sub 10, it's still going to be 4.795832. Okay. So this is how we use a graphing calculator to come up with our iterations here for x1 through x10. Okay, here's one more of these. Let's try ln of x plus 1 and then minus 3. And our initial approximation will be x is equal to, well, x sub 0 equal to 19.1. So that's x sub 0 here. So we need x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, x sub 8, all the way to x sub 10. Okay, we do need to do this. We need the derivative of f prime of x, f of x. So I'm going to write f prime of x over here. The derivative of f prime of x, well, the derivative of ln of x plus 1 would be 1 over x plus 1. And then the inside derivative, well, the derivative of x plus 1 will be 1, so it'll just still be 1 over x plus 1. That's what f prime of x is going to be. So now, x sub n plus 1 would be, well, better yet, let me do this at the bottom because it's going to take some space for me to simplify this. Let's see, x sub n plus 1, that's going to be x sub n minus, and in this case here, your f of x is that function right there, ln of the quantity x plus 1 minus 3, and that's going to be divided by 1 over x plus 1. That's your f prime of x. but I don't want to leave this fraction like that. So what I'm going to do here is multiply the numerator and the denominator by x plus 1. So this numerator will be multiplied by x plus 1. This denominator will be multiplied by x plus 1. Now, what's going to happen here is this. If I do the denominator times the denominator, what's going to happen is these x plus 1s are going to be gone. I'm going to be left with a 1 in the denominator. So here I'm going to have x of n minus, now the numerator, I'm going to pull the x plus 1 in front, and then that's going to be multiplied by this, ln of x plus 1 minus 3. That's going to be my new function here. Okay. Now my x sub 0, of course, that's going to be 19.1. That's given to us as the initial approximation. So the way I enter that in is to type this in. Type in the 19.1 and then hit the STO button to store it. And then I'm going to store that in xt theta n by pressing that button. And then press enter. Okay. So in this case here, clear this out, 19.1, hit the STO button, that's above the on key, that'll give you the right arrow, and then hit your xt theta n for the x, and then hit enter. You'll get the 19.1. So it's just saying that it's going to be stored in x. Now, I'm going to give you the keystrokes to enter all of this in. Okay? Now for the x sub n, let's use the xt theta button here. So this is what you'll type in. For the x, there'll be xt theta n, and then minus, and then left parentheses, x plus 1, wait a minute, correction here. Okay, this is what I did. I pressed the ln key, and then xt theta n for the x, plus 1, and then close the parentheses. And then minus 3, and then close the parentheses there. And then that's going to be times, because I'm going to multiply that by, and then left parentheses, xt theta n for the x, plus, and then 1. Because see, what I did was I put this part in first, and then the x plus 1. And then after that, you're going to STO to store that, and then press xt theta n, and then press enter. Okay. So these are the keystrokes that I'm using here. For this part right here where I got ln of x plus 1 minus 3, I type in xt theta. I type this in first. That's the x for the xt theta, minus, and then left parentheses, I did type this in. Xt theta n for the x, plus 1, close the parentheses. Oh, I forgot something. Let me start over. And then x, now minus, left parentheses, ln, press the ln key. It gives you the left parentheses, so xt theta plus 1, close the parentheses, and then minus 3, and then close your parentheses. And then press the times key to multiply that by, uh, left parentheses, xt theta for the x plus 1, close parentheses. And then we're going to press the STO button to store this into x, xt theta for the x, and then press enter. Okay. That's what I was looking for. Here you're going to get what x sub 1 is, 19.08553172. That's x sub 1. Now for x sub 2, go ahead and press enter again. And it'll give you, and I should round this off to 6 decimal places, 2, 3, 4, 5, 6. This would be 0.32. And then this right here will be your x sub 2 right here, 19.085537. And then hit enter again. That'd be 19.0. And notice that you're going to get the same number over and over again. Okay. And if I keep pressing enter, it's going to be the same for the remaining iterations here. So from x4 all the way down to x sub 10, it's going to be the same. So that tells me that the 0 for this particular natural log function would be 19.085537. Okay, so that's how we applied Newton's method to find the approximate zeros of any function. And this was long before we had graphing calculators. Okay, so I can tell you that when I was in school, in high school, taking AP calculus, we had to do all of this, fill in all that table to even come up with our approximate value. Okay, so that's all the section 4.8 that I need to cover in class on this video. I do need to mention some things to you before you leave. There is a quiz 5 on the MyLabs Plus system that is going to be open hopefully next week, or it should be open by now. The due date for that will be Friday, April the 20th at 11:59 p.m. So make sure you have that done. That quiz will be covering the material in section 4.4, 4.5, and 4.6. All right, your next exam, number 4, will be on Monday, April the 23rd. I will have a review sheet that covers the material in chapter 4. Okay, because on Monday we will do section 4.9, and that will wrap up chapter 4, which deals with antiderivatives. And a head note on this, the final exam will be on Wednesday, May the 2nd from 8 o'clock to 10 o'clock in the morning. It will be comprehensive. I will have a review sheet that will provide all the material that we discussed in this particular course. We might have to spend 2 days just reviewing for the final exam. Okay? All right, the homework should be available for you to complete on Newton's method. Do email me or call me if you have any questions. Have a good weekend.